you know that many of the stars twinkling in our night sky might already be dead? We're just seeing the last echoes of their light traveling for millions of years to reach us. It's a beautiful cosmic ghost story. But what really happens when a star dies? It's not a quiet fade to black. It's one of the most spectacular and violent events in the entire universe. Stick around, because we're about to journey into the heart of stellar death, from breathtaking explosions to the birth of the most mysterious objects in space. To understand how a star dies, we first have to understand how it lives. Imagine a star like our own sun. At its core, it's a gigantic nuclear fusion reactor. It spends billions of years fusing hydrogen atoms into helium, releasing an enormous amount of energy in the process. This energy pushes outward, creating a perfect balance against the immense inward pull of the star's own gravity. This delicate dance is what keeps a star stable, shining brightly for most of its life. But like any fuel source, the hydrogen in a star's core isn't infinite. So, what happens when it starts to run out? That's when things get really interesting. The star's life is a constant battle between gravity and energy, and when the fuel changes, the battle enters a new, dramatic phase. For stars similar in size to our sun, the end begins gracefully, but grows into something monstrous. Once the hydrogen in the core is used up, the fusion stops. Gravity, now unopposed, starts to crush the core. This compression heats the core up immensely, to the point where it becomes hot enough to start fusing the helium it created into heavier elements like carbon and oxygen. At the same time, a shell of hydrogen around the core gets hot enough to ignite. This double-barreled energy release is way more powerful than before. The star's outer layers swell up, expanding to hundreds of times their original size and cooling down, turning a brilliant, fiery red. The star has become a red giant. If this were our sun, it would swell up to engulf Mercury, Venus, and maybe even Earth. It's a terrifying and awe-inspiring thought. But the red giant phase doesn't last forever. The star's core continues to fuse helium, but eventually that runs out too. For a sun-sized star, there isn't enough mass and pressure to start fusing carbon. The star becomes unstable. It begins to pulsate, rhythmically expanding and contracting, and with each pulse, it sheds its outer layers into space. These layers of gas, enriched with elements like carbon and oxygen, drift away from the dying core. What's left behind is a beautiful glowing cloud of gas called a planetary nebula. It's a bit of a misleading name since it has nothing to do with planets. These nebulae are some of the most stunning objects we can see with telescopes, glowing with intricate shapes and vibrant colors. They are the star's final, beautiful side. At the center of this celestial artwork sits the star's collapsed core, a tiny, incredibly dense object called a white dwarf. A white dwarf is the true stellar corpse. It's about the size of Earth but contains the mass of our sun. A single teaspoon of white dwarf material would weigh several tons on Earth. This object is no longer producing energy through fusion. It's just a super hot ember, glowing with leftover heat. It will spend trillions of years slowly cooling down, fading from brilliant white to yellow, then to red, and finally becoming a cold, dark black dwarf, a lifeless chunk of carbon and oxygen floating in the eternal darkness of space. Our own sun is destined for this fate in about 5 billion years. It will leave behind a beautiful planetary nebula and a white dwarf to mark its place in the cosmos. It's a relatively peaceful end for a star, but not all stars get to die so quietly. For the real titans of the universe, the end is anything but peaceful. Now, let's talk about the heavyweights, stars that are at least 8 to 10 times more massive than our sun. These behemoths live fast and die young. They burn through their hydrogen fuel in just a few million years, not billions. When their hydrogen runs out, they also become giants, but on a much grander scale, they become red supergiants. Think of stars like Betelgeuse in the constellation Orion. If you placed it where our sun is, it would swallow all the inner planets and extend out past the orbit of Jupiter. Inside these supergiants, the process is far more extreme. The immense gravity allows the core to fuse heavier and heavier elements. After helium fuses into carbon, the Carbon fuses into neon, then oxygen, silicon, and so on, all the way up the periodic table until it creates iron. And iron is where everything goes catastrophically wrong. Fusing elements up to iron releases energy, which helps the star fight against gravity. But fusing iron doesn't release energy, it consumes it. The moment the core starts producing iron, the energy source that has held the star up for its entire life is switched off. In an instant, the outward pressure vanishes. Gravity wins, and it wins in the most dramatic way imaginable. The iron core, which is about the size of Earth, but with more mass than our Sun, collapses in on itself in less than a second. The collapse happens at 1/4 of the speed of light. The core shrinks from the size of a planet to the size of a city, becoming unimaginably dense. This sudden, violent collapse triggers a massive shockwave that rebounds outward. This shockwave slams into the star's outer layers, which are still falling inward, and triggers a monumental explosion. This is a Type 2 supernova. For a few weeks, the exploding star can outshine its entire galaxy, releasing more energy in an instant than our Sun will in its entire 10 billion year lifetime. The explosion is so powerful that it creates temperatures and pressures intense, enough to forge all the elements heavier than iron, gold, silver, platinum, uranium. Every bit of gold in your jewelry, every bit of silver was forged in the heart of a supernova explosion billions of years ago. We are literally made of stardust, but the most precious elements in our world are forged in these final, violent moments of a massive star's death. The supernova blasts these newly created elements across the galaxy, seeding space with the raw materials for new stars, new planets, and potentially new life. So what's left behind after this cosmic fireworks show? It depends on the mass of the original star's core. If the core is between about 1.5 and 3 times the mass of our Sun, the collapse is so intense that protons and electrons are crushed together to form neutrons. The entire core becomes a giant ball of neutrons, packed together with no space between them. This is a neutron star. Like a white dwarf, it's incredibly dense. A neutron star is only about 12 miles in diameter, the size of a city, but it contains more mass than our Sun. A single sugar cube of neutron star material would weigh as much as all of humanity combined. They also spin incredibly fast, sometimes hundreds of times per second, and have magnetic fields 1 trillion times stronger than Earth's. Some neutron stars, called pulsars, sweep beams of radiation across space like a cosmic lighthouse. But what if the star is even more massive? What if the collapsing core is more than 3 times the mass of our Sun? In that case, not even the pressure of neutrons can stop the collapse. Nothing can. Gravity becomes an unstoppable force. The core continues to collapse forever, crushing itself down into an infinitely small, infinitely dense point called a singularity. It punches a hole in the very fabric of space-time itself. This creates an object with a gravitational pull so strong that nothing, not even light, can escape it. A black hole is born. The boundary around a black hole from which nothing can escape is called the event horizon. Crossing it is a one-way trip. The death of the most massive stars in the universe creates the most mysterious and extreme objects in the cosmos. So, from the quiet fading of a white dwarf to the universe-altering explosion of a supernova and the birth of a black hole, the death of a star is not just an ending. It's a crucial part of the cosmic cycle of life and death. The elements created and scattered by dying stars form the next generation of celestial bodies. The carbon in our bodies, the oxygen we breathe, the iron in our blood, it was all cooked up inside a star and flung across space in its death throes. So next time you look up at the night sky, remember you're not just seeing distant points of light. You're seeing the past, present, and future of the universe. You're seeing the ghosts of stars that died long ago, the life of stars burning brightly now, and the cosmic nurseries where their remains will one day give birth to something new. The universe is a story of creation born from destruction. Thank you so much for joining me on this journey through stellar death. If you found this as fascinating as I do, make sure to hit that like button and subscribe for more deep dives into the cosmos. Let me know in the comments which part of a star's death you find most mind-blowing. Until next time, keep looking up.